Yes, good morning students. Good morning to all of you. So in previous class, we are discussing about thermodynamics chapter. Okay, yes. And in previous class, we have discussed some basic definitions. What is system, what is surrounding, what is thermodynamic variables, what are different types of thermodynamic systems, and what are the different types of thermodynamic processes like isothermal process, isobaric process, isochoric process, adiabatic process, cyclic process, quasi-static process. Some six processes we have discussed. No? Yes. And after that, we discussed about indicator diagram. What is that one, Anna? Indicator diagram. We have discussed about this also. What is indicator diagram, Anna? Indicator diagram means nothing but it is a graphical representation of any process. In that process, we will take any two variables. Let us suppose pressure and volume. Pressure let us take on y-axis and volume let us take it on x-axis. Then what is happening to the system? Let us suppose volume is increasing with decreasing pressure. Let us suppose the process is happening like this. Let us suppose. So here what is happening, Anna? This is the initial state. This is the final state B. One gas is undergoing expansion, let us suppose. Now in this expansion, initially volume is this much, but final volume become this much. See, this much final volume. Means volume has increased. At the same time, this is the initial pressure, this is the final pressure. Means pressure has decreased. Means it is one process. This process we have indicated with a graphical representation. That graphical representation of any process, whatever it may be, that process we call that diagram we call it as indicator diagram. Clear? Yeah, it is important. We will discuss again about this one later. Okay. Yes. Next, after that, we discussed about work done by a gas. No. Yes. Work done by a gas. What is the formula for work done by a gas? Let us discuss one more time. Let us suppose here we are having one cylinder. Let us suppose this is one cylinder we are having. Okay. Now in this cylinder, in this cylinder, let us suppose we are having one piston. Let us suppose yes, like this one piston is there with us now. This piston area of cross section, let us suppose capital A area of cross section piston is there with us. Let us suppose now if this in this let us suppose there is one gas is filled whose pressure is P and volume is V. Here gas is there. Okay, now let us suppose some heat energy is given to this gas. Some heat energy is supplied to gas. What happened? Gas will expand. No? Yes. This gas will expand. While it is expanding, this gas will exert some pressure on this piston. Due to that pressure exerted by the gas on the piston, a force will act in upward direction. Due to that force, this piston moves to some distance. Let us suppose the piston has traveled from here to here. Who is this Preeti? Why have sent message like Hi Rami? What Preeti? Preeti. If you repeat it next time, I will not allow you to enter to my meeting room. Why you have sent? Listen class. Let us suppose this piston has traveled a distance dx. Okay. Yes. Now, one minute wait, Nana. Sorting option where is it? Okay, yes. Now, a force will act, and that force is from where I can get this. Yes. Now, this force is nothing but pressure of the gas into area of cross section on which area this pressure is acting. Yes, on this area of cross section, this pressure is acting. Clear? Now this much force is acting. Now this force, that is force due to the pressure, is moving the piston by a distance dx. So due to that small displacement of the piston, small amount of work is done on the piston by the gas. That is force into displacement. Clear? Yes. Now this small amount of work done can be written as force. What is the pressure due to gas and area of cross section of the piston into dx. Clear? Yes. So dw is equal to pressure due to gas into area of cross section into dx. What is this, Nana? Area into distance is nothing but volume. Means this piston traveled from here to here. So how much volume it has displaced means dv. Clear? Yes. Small amount of work done due to a gas, we can give like this. dw is equal to pdv. Clear? Now let us suppose piston has traveled by a distance dv. Then total work done by the gas we can give by integrating this. Means integration of pdv. Clear? And here we are integrating volume. So volume limits, if you apply initial volume to final volume. Let us suppose initial volume is v initial, final volume is v final. Yes, this will be the formula for work done by the gas. Clear? Important formula, you need to remember this now. Clear? Okay. Yes. Now let us go to very important law of thermodynamics. That is first law of thermodynamics. Nana. First law of thermodynamics. Very important, Nana. They may ask you this statement, simply this statement in your board exam, and on these statements you will have so many competitive exam questions also you may get. Means JE and NEET, you will get so many questions they can frame on this concept. Let us discuss about this one. See, let us suppose, imagine that we are having one container. Let us suppose we are having one container. Let us suppose like this, one container is there with us. Okay. Now, let us suppose this container is filled with one gas. Let us suppose one gas is filled in this container. Okay. Now, this is what gas. Now, for this gas, let us suppose we have given some heat energy to it. Some heat energy we have supplied to this. How we will give heat energy? Let us suppose here this container is placed on a stove. Clear? Means some heat energy we are supplying to this gas. Some Q we are adding to this gas. Some heat energy we are supplying to the gas. So what will happen, Nana, to this gas? What will happen? Think what will happen. One thing, gas can expand. Clear? Yes, we know. First point, what are the various points we will get? Gas can expand. Second point, what will happen, Nana? Temperature of the gas will change. Correct? After some time, if temperature increases more than 100 degrees centigrade, something else, already it is in gaseous state, it will be in gaseous state only. Means these are the two things it may happen to the gas. We know that internal energy of a gas is nothing but kinetic energy of a gas, and we know kinetic energy depends upon temperature. Already I informed you. Means if temperature of a gas increases, means internal energy of a gas increases. Means by supplying some heat energy to the gas, what we are doing, we are increasing the internal energy of a gas. Second thing, what will happen? See, this gas will expand. This gas will expand. Means, let us imagine one piston is placed here. Let us imagine here one piston is placed. Let us suppose like this one piston is placed here. Now, when this gas is expanding, whose area of friction is A, when this gas is expanding, this piston from here to here, it will move by some distance, no? That means this gas is doing some work. It is performing some work when the gas is expanding. Means whatever the heat energy that you are supplying to the gas, that heat energy is utilized in increasing the internal energy of a gas, and remaining amount of heat energy will be utilized to perform work on its surrounding. Means this system, this piston is the surrounding which is in contact with the gas. On that surrounding, this gas will perform some work. Okay, that is formulated like this. The heat energy supplied to the gas will be equal to sum of internal energy of a gas, increase in internal energy of a gas, and work done by the gas. This equation, this statement is called as first law of thermodynamics. Did you understand? Very easy, no, it is. Clear? Okay, what is first law of thermodynamics? Whatever the heat energy that we will supply to the gas, that heat energy, by taking the heat energy, gas, what it can do? One thing, temperature of a gas may increase. Second thing, gas may expand. While it is expanding, it will perform some work on these surrounding systems. Clear? So due to that reason, we can say the heat energy that is supplied to the gas is utilized in increasing the internal energy of a gas and in performing work done by the system on the surrounding. Clear? So mathematically we will write this one like this. Clear? So according to first law of thermodynamics, the heat energy that is supplied to the gas is utilized in increasing the internal energy of a gas and in performing some work done on the surrounding. First law of thermodynamics. Okay, now while using this first law of thermodynamics, we need to have some sign convention. Means whether heat energy to be taken as positive or negative, when we have to take du, when we have to take positive or negative, dw, when we have to take positive or negative. These points are very important. So first point, see, if heat is supplied to the gas or any system, you can take gas or any system, not only gas, any system, then that heat energy we have to take it as positive. Clear? If heat is absorbed, if we take heat energy from the system, from the gas or any system, then we should take that heat energy as negative heat energy. Are you understanding? Clear? Next, about internal energy. If temperature increases, that implies internal energy should be taken as positive. If temperature of any system or surrounding any system of any gas, if it increase, then we should take it as positive. Okay, and if temperature decreases, then we should take it as negative. Internal energy we should take it as negative. Clear? Okay, what about work done? If gas expands, means what is that meaning? Gas is expanding means gas is performing some work on the surrounding. That means work is done by the gas. Therefore, work done we should take it as positive. If work is done by the gas or work is done by the system, then that work done we should take it as positive. Okay, and if gas compressed, that is work is done on the system or gas, then that work done we should take it as negative. These are the 3 points that we need to remember. See, first point what na? Yes, first law of thermodynamics. What it states that heat energy that is supplied to the gas is equal to sum of increase in internal energy of a gas and work done by the gas. The heat energy supplied to the system is equal to sum of increase in internal energy of a system and work done by the system. Clear? Here dq we should take it as positive when heat is supplied to the gas. dq we should take it as negative when heat is absorbed from the gas. du we should take it as positive when internal energy is increasing, means temperature is increasing. du we should take it as negative when internal energy is decreasing. dw we should take it as positive when work is done by the system or by the gas, means during expansion of a gas. We can take example. dw we should take it as negative when work is done on the system or on the gas, that means when the gas is compressed. dw should be taken as negative. Clear? Yes. So these are the points that we need to remember about first law of thermodynamics. See, first law of thermodynamics, it says that dq, heat energy supplied to the system, is equal to sum of increasing internal energy of the system and work done by the system. Just now I have given one formula for work done by the system, that is dw is equal to what? PdV. Clear? Yes. So that implies first law of thermodynamics, it will become du plus pdv. Why I am writing du plus pdv? Understood? No, because dw, work done by any system or any gas, we can write in the form of pressure and volume as p into dv, pressure into change in volume, pressure into change in volume. Clear? This is also first law of thermodynamics. Clear? Are you understanding? Okay, very easy point. Got it, students? Yes. Next. Now let us discuss about indicator diagram one more time. See, let us suppose we are having one indicator diagram like this. Let us suppose one indicator diagram is there like this. Okay. On x-axis, let us take volume, and on y-axis, let us take pressure. Okay. Yes. Now let us suppose we are having one process. In that process, volume is changing like this. Let us suppose this point is A, this point is B. Let us suppose volume is changing like this. How it is changing from A to B? Like this. Means what is happening to it? As we are moving from A to B, volume is increasing. Means gas is undergoing expansion. Means we can say it as work is done by the system. Gas is expanding. Work is done by the gas. Then gas will expand. Okay. Yeah. So in this diagram, we should take work done as positive. Just now I discussed. Okay. Now let us find what is the work done by the gas in this, by using this indicator diagram. How to find? Simple technique, Nana. See, as you are moving like this, pressure is not constant. Pressure is decreasing, decreasing. So that's why what we will do, no, this one, this we will divide into small strips, like what we did in work done by variable force. How we did, same as it is. Let us divide this into small strips like this. Let us divide. Clear? Yes. Now let us take at any volume, let us take one strip. Let us take this strip. Let us take, I am taking this strip. Okay. Now in this strip, let us give a name for this: A dash, B dash, B. This is one strip I am having now. Okay. For this strip, A dash is nothing but B dash. This we can take pressure due to gas. And AB is nothing but A dash B dash. If we take this as change in volume from A dash to B dash, how much volume is changing? That we will take. Then small amount of work done can be given as area under this curve. Clear? Area under A dash B dash curve. This area is nothing but length into breadth. Length is what is there, Nana? A to A dash. How much it is? P. Breadth how much, Nana? dV. Clear? Yes. Now, small amount of work done can be given like this. Now, if you want to get total work done from here to here, if you want to get total work done, what will you do? Integrate it. We'll get total work done. Integration from where to where we need to do? From here to here. This is initial volume V1, let us take. This is final volume V2, let us take. Then it can be given from V1 to V2 like this. This will be the total work done. Did you understand? Clear? If I give one statement like this, see here, let us suppose here we are having one indicator diagram like this. Okay. And the indicator diagram is like this. This is pressure and this is volume. Clear? Yes. Let us suppose this volume is up to here. This is the origin. This is volume is 2V. Now, what is the work done by the gas? What you will do? Area under this graph. Area under this graph. Okay. Are you understanding, students? Clear? Now, this area, how can we write now? This length into this breadth. Length, let us suppose here pressure is P. This length how much now? P to 0 is P. And breadth how much now? 2V. So this will be the work done. Means 2PV is the work done. Are you understanding? If the curve is given like this, arrow mark is given like this, means what is happening? Volume is increasing. That means we can take it as positive work done. Clear? If the same graph, same, everything is same, let us take. Same graph, here pressure P, here volume 2V, let us take. And graph is like this. Then what will be the work done? Again, work done is equal to area under the curve, area under this curve. This is length is P and width is 2V. It will be 2PV. But see here, it is undergoing compression. Volume is decreasing. So that's why we should take it as negative. Clear? Are you understanding? Clear? Yes. Now come to that point, indicator diagram. Where it is? Here. See, what is the importance of this indicator diagram? By using indicator diagram, we can find work done by the gas or system. How? By taking area under the curve. Are you understanding? Clear? Okay. Any doubt in this? Yes. Now let us take one. Sorry. Yeah. Let us take one cyclic process. Cyclic process. Let us discuss about cyclic process. No? What is cyclic process? Any thermodynamic process, if it starts from one state, again if it comes back to the same state, then that process is called as a cyclic process. Clear? Yes. Now, see, let us take one indicator diagram here. I am taking one indicator diagram here. This is x-axis and this is y-axis. This is the origin. Okay. Now let us take one process in which, like this one process. Let us imagine a process is starting from point A, and first it is expanding, then it undergoes like this one process and came back to same process like this. Let us suppose this is the process which is occurring. A, B, C, D. Let us suppose A. A, B, C, D, A back is one cyclic process. From which state it has started, again to the same state we came back. Okay. Now let us imagine here pressure is here this point. Pressure is P1. At this point, pressure is P2. Means this is a pressure axis, and this is the volume axis. Let us suppose at this point volume is V1 and here volume is V2. Let us suppose. Okay, clear? Yes. Now see, first thing, from point A to B, when any system, if it undergo from A to B process, A to B, now we are having from A to B, graph is going like this, from A to B. From A to B. This is the total graph on total area under the graph. This is the total area under the graph. Are you getting clear? Okay. This area gives you what? Work done by the gas. Clear? From A to B, work done by the gas is what? Area under the graph, and that too it is in expanding. See, volume is increasing. Clear? Yeah. So this area, how much we can get? How much we can get? Nana? See, this length A to B, or this is the length you take. This length how much? Nana? This total length P1. It is starting from the origin. No, yes. And breadth how much? Nana? From here to here, V2 minus V1. V2 minus V1 is the breadth, and the 2 it is positive. Clear? Okay. Yes. Now from C to D, what is happening? Let us see. C to D, what happens? Let us see. C to D, this area. Can you see this area with this mark lighted? No, we can't. Yes, this area you see. C to D area, this area. C to D, what is happening, Nana? Work done, let us find. Work done is area under the graph. This area, how much? This length. What is this? P2 into change in volume, how much? Nana? V2 minus V1. But it is positive or negative? Negative work done because it is compressing. Clear? Now, total work done, how much? Total work done can be written as total work done area under this total graph. Nothing but W1, this is W2, this is W1 plus W2. But what is W1? W1 is P1 into V2 minus V1 plus W2 is what? Minus P2 into V2 minus V1. Then what we can write this one? V2 minus V1, let us take common. We will get P1 minus P2. Yeah, see here, this is V2 minus V1. This one. This is V2 minus V1. Then what is P1 minus P2? This is P1 minus P2. That means if you take any cyclic process, work done, total work done will be nothing but this into this. What is these two? That is area under this closed graph. In this closed graph, how much area is there? That area. Clear? Are you understanding point what I am saying? This total area is nothing but work done by a cyclic process. And that too, this work done is either it can be positive, it can be negative. If the cyclic process is taken in clockwise sense, like this clockwise sense, if it is there, then work done will be positive, pressure graph, volume graph. Whereas if the indicator diagram anti-clockwise sense like this, then work done will be negative, Nana. That just these 2 points, just you remember these 2 points. Clear? Okay. Did you understand these points? So what is the work done in a cyclic process by using indicator diagram? It is nothing but area under the curve, closed curve, and that's too, if a closed curve is in clockwise sense, then it is positive work done. If a closed curve is in anti-clockwise sense, then it will be called as negative work done. Did you understand? Clear? Okay, students? Yes. Now, let us take one example on first law of thermodynamics. See, first law of thermodynamics gives you what? dq is equal to du plus work done. Clear? Yes. All of you take one pen and paper. I am giving you one question. Question is, I am giving you, suppose 50 joules of heat energy is supplied to the gas. Then work done on the gas is 20 joules. Then find change in internal energy of the gas. Can you find this answer? I have given time for you. You have to calculate. I have explained each and everything. Fast, give me answer. You can send answer now. 30, Lalit Kumar. 30 joules. Good. 30 sir, 30 sir, 30 sir. Yes, let us check how it is. Okay, Anna. Let us check how it is. Answer. See, 50 joules. What is happening? Heat is supplied to the gas. So dq value how much? Dq value is plus 50 joules. Okay. And what is 20 joules? It is work done on the gas. So this work done, we should take it as positive or negative? We should take it as negative because it is work done on the gas. No, see here I have written. Where I have written? Work is done on the system. Negative. Clear? Yes. So it is negative. How much? 20 joules. Okay. According to first law of thermodynamics, dq is equal to du plus dw. dq how much given? 50 is equal to du is du we need to find plus dw how much? Minus 20. So what you will get? 50 is equal to du minus 20. So du is equal to how much? 50 plus 20, no? Total 70 joules. See, you have given wrong answer. Why now changed? Good. Michelle, Lalit Kumar. Good, good, good. You need to consider sign. According to sign, we should get. Did you understand now? Here, let us take one more question. 1 minute time is there. Let us take one more question. Okay. Yes. Question number 2. Work done by the gas is 30 joules and increase in internal energy of gas is 20 joules. Then what is the heat energy supplied to the gas? Answer. Seconds, within seconds you can give this answer. Yes, one answer I got. Observe 50 joules. Michelle 10 he said. Away 50. 50 is right answer. Na? Observe good. Away good. Sneha good. Amruta good. Good. Yes. So why? Why 50 joules? Rani 10 is wrong answer. See, 30 joule is what? Na? Work is done by the gas. So work done should be taken as positive. Plus 50 joules. And 20 joules is what? Internal energy of a gas increases. So du is what? Plus 20 joules. dq what they are asking? dq is equal to du plus dw. du is given 20 joules plus 20 plus dw is plus